17 volcanoes, not one, not a cluster, 17 separate volcanic systems, distributed across the Pacific Ring of Fire from Chile to the Philippines, all entering states of elevated activity within the same 18-month window. Scientists have a word for when multiple volcanoes activate in a short period across a wide geographic region. The word is not coincidence. The word is forcing, as in something is forcing the system. Something external to the volcanoes themselves is applying pressure across the entire network simultaneously. Tonight, we are going to talk about what that forcing mechanism is. We are going to talk about El Niño, not the version you learned about in school that brings rain to California and drought to Australia, but the version that the volcanological community has been quietly, carefully studying for 2 decades. The version that changes sea level, that alters the weight of ocean water pressing down on the seafloor, that adjusts by millimeters and centimeters the pressure load on some of the most dangerous volcanic systems on Earth. And then we are going to talk about the part that is worse than 17 volcanoes activating at once. Because the volcanoes are not the story. The volcanoes are the symptom. The story is what El Niño is doing to the systems that connect them. Before we begin, if you are here because you want the data, not the drama, hit like and subscribe. This channel does not traffic in panic. We traffic in evidence. Tell me in the comments where you are watching from tonight. And tell me this, did you know that ocean temperature patterns could influence volcanic activity? Because most people don't. And by the end of this video, you will understand exactly why that gap in public knowledge matters now. Let's get into it. Let me give you the list. Not because a list is dramatic, though it is, but because each entry on it is a data point. And data points, in aggregate, tell a story that individual events do not. In the 18-month period between January 2024 and June 2025, the following volcanic systems entered states of elevated activity, renewed eruption, or significant unrest after periods of relative quiet: Villarrica, Chile; Popocatépetl, Mexico; Nevado del Ruiz, Colombia; Sangay, Ecuador; Mount Marapi, Indonesia; Lewatobi Laki-Laki, Indonesia; Ibu, Indonesia; Dukono, Indonesia; Tal, Philippines; Bulusan, Philippines; Mount Canlaon, Philippines; Manam, Papua New Guinea; Bagana, Papua New Guinea; Taverver, Papua New Guinea; Vanuatu's Ambae; Stromboli, Italy; and Kilauea, Hawaii. 17 systems, 7 countries. A geographic arc stretching more than 20,000 kilometers. Now, some caveats are essential here, because intellectual honesty requires them. The Pacific Ring of Fire contains approximately 452 active volcanoes. At any given moment, somewhere between 40 and 50 of them are in some state of activity. The baseline level of global volcanic activity is not zero. Some of the 17 systems on that list are frequently active. Dukono in Indonesia, for example, has been in near-continuous eruption for decades. Popocatépetl has been active since 1994. Kilauea's current eruption cycle has been running in various forms for years. So the question is not simply whether these volcanoes erupted. The question is whether the pattern, the timing, the coincidence, the geographic distribution represents something statistically meaningful. Whether 17 systems entering elevated states simultaneously represents a signal above the background noise of a planet that is always, somewhere, erupting. And the answer, according to a growing body of peer-reviewed research, is yes, with a specific mechanism, a specific driver, and a specific physical explanation that turns out to be one of the more counterintuitive ideas in all of Earth science. The driver is El Niño. And to understand how a sea surface temperature anomaly in the Central Pacific can influence volcanic eruptions on 5 continents, you first need to understand what El Niño actually does to the physical planet. Was what happened across the Pacific Ring of Fire in 2024 and 2025 a coincidence? Or was it a forced response to a global climate pattern that the scientific community has been tracking for decades? That question changes how you think about everything that follows. Most people know El Niño as a weather pattern. Warm water in the Central and Eastern Pacific, altered jet streams, wet winters in the American Southwest, drought in Australia and Southeast Asia. El Niño years are associated with elevated global average temperatures, disrupted agricultural patterns, and increased frequency of extreme weather events. That understanding is correct as far as it goes, but it stops at the atmosphere. It treats El Niño as a phenomenon that begins at the ocean's surface and expresses itself in the air above it. The volcanological research doesn't stop at the atmosphere. It goes down. Here is the key physical fact that most El Niño coverage misses entirely. El Niño doesn't just change where warm water sits on the surface of the Pacific. It changes how much water is where. It physically redistributes the mass of the ocean. During a strong El Niño event, warm water that is normally piled up in the Western Pacific, held there by trade winds that push surface water westward across the ocean, relaxes. The trade winds weaken, the warm water sloshes eastward, the Western Pacific sea level drops, the Eastern Pacific sea level rises. We are not talking about small numbers here. During the 1997-1998 El Niño, one of the strongest on record, sea level in the Western Pacific dropped by approximately 20 to 30 centimeters relative to the Eastern Pacific. During the 2015-2016 El Niño, similar patterns were recorded. During the 2023-2024 El Niño, which is the event most directly relevant to the volcanic activity we are discussing, measurements showed regional sea level anomalies of 15 to 25 centimeters across the Western and Central Pacific. 25 centimeters. That is the depth of water being removed from above, some of the most volcanically active seafloor on Earth now. Here is where the volcanology comes in, and here is where it gets counterintuitive. Water is heavy. A column of seawater 1 meter deep, covering 1 square kilometer, weighs approximately 1 billion kilograms. 1 billion kilograms. The ocean above a subduction zone, above the seafloor that sits at the top of a volcanic system, is not just water. It is a load. It is pressure. It is weight pressing down on the crust below it. When El Niño removes 20 to 25 centimeters of water from the Western Pacific, it is not just changing the sea level. It is reducing the pressure load on the seafloor beneath that region. It is taking weight off the lid, and volcanic systems, specifically the hydrothermal and magmatic systems that feed the volcanoes of the Pacific Ring of Fire, are sensitive to pressure changes, not in the crude mechanical way of a pressure cooker, but in the subtle, physical way of a system that is already at or near a critical pressure threshold. A system where small changes in the external pressure load can tip the balance between continued containment and upward migration of magmatic fluids. The scientific term for this is volcanic unloading, and the research documenting its effects is more robust than most people realize. Was El Niño the trigger for the 17? Or is the connection between ocean mass redistribution and volcanic activity a correlation without causation? To answer that, we need to look at what the data actually shows across the historical record. The connection between surface loading changes and volcanic activity is not a new idea. It has been studied in several distinct contexts over the past 3 decades. The most well-established version of the loading volcanism connection comes from glaciology. The relationship between glacial retreat and volcanic activity in Iceland has been documented extensively. As Iceland's glaciers lose mass, as millions of tons of ice melt and flow into the ocean, the pressure on the underlying crust decreases. The crust rebounds upward. The magmatic systems beneath Iceland, freed from the weight of the ice above them, show measurable increases in activity. This is not a fringe idea. It is peer-reviewed, replicated science. A 2010 paper in Geophysical Research Letters documented a clear correlation between accelerated glacial unloading in Iceland and increased magma production rates in Icelandic volcanic systems. The mechanism is straightforward. Lower pressure above the mantle reduces the melting point of mantle rock, increasing the rate at which it partially melts and generates magma. The Yellowstone research community has documented stores it. There are 4 systems in the Pacific Ring of Fire that the monitoring community has been watching with elevated concern during, and after the 2023-2024 El Niño, and that showed clear signs of responding to the oceanic loading changes without producing major eruptive activity. The first is Campi Flegrei in Italy, technically not in the Pacific, but responding to the same global geophysical trends. Campi Flegrei, the volcanic caldera that underlies the western suburbs of Naples and has 3 million people living within its potential hazard zone, has been in a state of continuous inflation since 2005. The inflation rate has accelerated. The ground in the Pozzuoli area has risen by more than a meter since the current unrest episode began. Seismicity has increased. Gas emissions have elevated. And in 2023 and 2024, the rate of both deformation and seismicity showed a measurable uptick that the Vesuvius Observatory has been monitoring with what it describes, in careful institutional language, as close attention. Campi Flegrei has had 2 major eruptions in the past 40,000 years. The Campanian ignimbrite eruption approximately 40,000 years ago was one of the largest volcanic events in European geological history. The Monte Nuovo eruption in 1538 demonstrated that the system is capable of reactivating after long dormancy with minimal warning. The second is the Taupo volcanic zone in New Zealand. The Taupo supervolcano last erupted in approximately 232 CE, producing what is considered the most violent eruption of the past 5,000 years. The monitoring network around Lake Taupo detected an unusual earthquake swarm in 2022, followed by elevated seismicity in 2023 and 2024 that was correlated in time with the El Niño event. New Zealand's GeoNet raised the volcanic alert level for Taupo from level 0 to level 1 in 2022, the first time in the modern monitoring era that the system was officially placed in a state of unrest. The third is the axial seamount system in the northeastern Pacific, a submarine volcano on Juan de Fuca Ridge, approximately 480 kilometers off the coast of Oregon. Axial is not a threat to human populations in the conventional sense, but it is one of the most carefully monitored submarine volcanic systems on Earth, and its behavior is directly sensitive to oceanic loading changes. The 2015 El Niño was followed by an axial eruption in April 2015. The 2023-2024 El Niño produced a similar pattern of elevated seismicity and inflation at axial that the University of Washington monitoring team described as consistent with pre-eruptive conditions. The fourth, and this is the one that deserves the most extended discussion, is the Alaska Peninsula and Aleutian Islands volcanic arc. The Aleutians host 52 volcanoes that have been active in the last 300 years. Several of them erupted or showed elevated activity during the 2023-2025 window. But the one the Alaska Volcano Observatory has been watching most carefully is not one that erupted. It is one that didn't. The Aniakchak caldera in the Alaska Peninsula last erupted in 1931. Prior to that, its most recent major eruptive episode, approximately 500 years ago, was one of the largest volcanic events in the Holocene, the geological epoch that began at the end of the last ice age and encompasses all of recorded human history. The 3,500-year-old Aniakchak eruption deposited ash across Alaska, Canada, and Greenland. The Alaska Volcano Observatory recorded elevated seismicity at Aniakchak beginning in late T23. The swarm was not large, it was not publicized, but it was noted. None of these four systems erupted during the El Niño window, but all four showed measurable responses to the same geophysical forcing that drove the 17 eruptions. They are springs that were compressed. They did not fire, they are waiting. Was the El Niño a trigger for a one-time release of accumulated volcanic stress across the Pacific? Or was it a perturbation of a system that is still accumulating stress? A system that will respond again to the next El Niño, and the one after that, each time from a higher baseline of accumulated pressure? Here is the part that is worse than 17 volcanoes. Here is the part that, when I first encountered it in the literature, required me to read it 3 times before I accepted that the mathematics were really saying what they appeared to be saying. The story of El Niño and volcanic activity is not just a story about what El Niño does to volcanoes. It is a story about what volcanoes do to El Niño, and what they do, what volcanic eruptions, particularly the large ones that inject material into the stratosphere, actually do to the climate system. Creates a feedback loop that the standard El Niño models do not fully incorporate. When a large volcanic eruption injects sulfur dioxide into the stratosphere, that gas reacts with water vapor to form sulfate aerosol particles. Those particles are highly reflective. They reflect incoming solar radiation back into space before it can reach the Earth's surface. The result is a temporary cooling of the Earth's surface, a volcanic winter in the extreme cases, or a modest cooling in the range of 0.1 to 0.5 degrees Celsius for moderate eruptions. That cooling is not distributed uniformly. It is strongest over land and at higher latitudes, and it interacts with the pre-existing patterns of the climate system in ways that are specific and predictable. One of those interactions is with El Niño itself. Research published in the journal Science in 2019 examined the historical relationship between large volcanic eruptions and ENSO patterns using paleoclimate records going back 1,000 years. Their finding was striking. Large northern hemisphere volcanic eruptions are followed, with high statistical reliability, by El Niño conditions in the tropical Pacific within 1 to 2 years of the eruption. The mechanism runs like this. Volcanic cooling of the northern hemisphere land masses alters the temperature gradient between the tropics and the mid-latitudes. This gradient drives the atmospheric circulation patterns, the Hadley cells, the trade winds, that normally maintain the La Niña-like state of the tropical Pacific. When the gradient changes, the trade winds weaken. Warm water moves eastward, El Niño develops. Now, hold that in mind, and consider what it means in the context of what we have just discussed. El Niño produces sea level changes that reduce oceanic loading on Pacific volcanic systems. Reduced loading increases volcanic activity. Increased volcanic activity injects sulfate aerosols into the stratosphere. Stratospheric aerosols produce asymmetric cooling that weakens trade winds. Weakened trade winds produce El Niño conditions. El Niño produces sea level changes. Read that again. El Niño drives volcanic activity. Volcanic activity drives El Niño. It is a loop, a geophysical feedback cycle connecting ocean circulation, atmospheric dynamics, and volcanic activity in a relationship that was not included in the major coupled climate models until very recently. A relationship that, when incorporated into those models, changes the projected behavior of the system in ways that the modeling community has been quietly working to understand. The 2023-2024 El Niño produced elevated volcanic activity across the Pacific. Some of those eruptions injected measurable quantities of sulfate aerosols into the stratosphere. Those aerosols are producing a modest cooling signal, masked right now by the general warming trend, but present in the data. That cooling signal is affecting the atmospheric circulation patterns that drive ENSO. The question being asked in the climate modeling community right now is not whether the feedback is real. It is demonstrably real. The question is whether the current state of the climate system, with its elevated baseline temperatures, its altered jet stream patterns, its degraded sea ice, has changed the strength and character of the feedback in ways that the historical record cannot fully capture. Because the historical record of El Niño volcanic feedback was established in a climate that is not the climate we have now. The 0-year paleoclimate record of that feedback was generated in a world where Arctic sea ice covered a significantly larger area, where the temperature gradient between tropics and poles was steeper, where the atmospheric circulation patterns were operating within a different energetic regime. The feedback exists. Its historical behavior is documented. How it behaves in the climate of 2025 and beyond, in a world 2 degrees warmer than the pre-industrial baseline, with Arctic sea ice at record lows, with jet stream patterns measurably altered from their historical norms, is genuinely unknown. That unknown is the worst part. Not the 17 eruptions, not the 4 systems that absorb the forcing without releasing, not even the feedback loop itself. The worst part is that we are operating a system we do not fully understand, in a state it has never previously been in, and the models we use to project its future behavior were built on a history that no longer fully applies. Let me shift the frame for a moment, because there is a human dimension to this story that the geophysics alone doesn't capture. The 17 volcanic systems that showed elevated activity during the 2023-2024 El Niño window are not located in convenient places. They are not erupting in empty deserts or uninhabited archipelagos. They are erupting in some of the most densely populated volcanic hazard zones on Earth. Popocatépetl in Mexico stands 70 kilometers from Mexico City, a metropolitan area of more than 21 million people. The volcano has been in a state of elevated activity since 1994, producing what volcanologists call volcanic eruptions, explosive bursts that send ash and pyroclastic material to altitudes of several kilometers. During the 2023-2024 El Niño window, activity at Popocatépetl intensified to levels that prompted multiple ashfall alerts for communities in the states of Puebla, Morelos, and Mexico State. Taal volcano in the Philippines sits inside a lake that itself sits inside a larger caldera, a volcanic system nested within a volcanic system on the island of Luzon, one of the most densely populated islands in the world. The 2020 Taal eruption, which occurred notably during a strong ENSO transition period, forced the evacuation of over 300,000 people in 24 hours. During the 2023-2024 window, Taal showed elevated phreatomagmatic activity, steam-driven explosions, and ground deformation consistent with renewed pressurization of the shallow magmatic system. Nevado del Ruiz in Colombia is perhaps the most sobering entry on the list, because it carries a specific and terrible history. In 1985, Nevado del Ruiz erupted in a moderate eruption, not even a large one by geological standards, that generated lahars, volcanic mudflows, which traveled down river valleys and buried the town of Armero. The death toll was approximately 23,000 people. It remains the deadliest volcanic disaster in the Western Hemisphere in the 20th century. During the 2023-2024 El Niño window, Nevado del Ruiz entered its highest alert level since the Armero disaster. The Colombian Geological Survey raised the alert to orange, 1 level below red, the highest possible, based on increased seismicity, accelerated ground deformation, and elevated sulfur dioxide emissions. An eruption was considered probable. The Colombian government issued evacuation orders for communities in the potential lahar pathways. An eruption of comparable magnitude to 1985, with 2025 population densities in the Lagunillas River Valley, could kill more people than Armero. The infrastructure that channels lahar flows has not been comprehensively upgraded in 40 years. The population in the hazard zone has grown. Ruiz did not produce a major eruption during the window. The activity subsided. The evacuations were partly reversed. The alert level was eventually reduced. The distribution of volcanic monitoring resources globally correlates economic wealth of the countries where the volcanoes are located than with the size of the populations at risk or the magnitude of the geological hazard. The United States, Japan, Italy, and New Zealand have world-class volcanic monitoring networks. Indonesia, which has 147 active volcanoes and a population of 270 million, many of whom live in volcanic hazard zones, has a National Volcano Monitoring Agency, PVMBG, that does competent work, but is chronically under-resourced relative to the scope of the hazard it manages. The Philippines, with its 17 active volcanoes, its 110 million people, and its specific vulnerability to Tal and Mayan as FIVOLCS, a capable agency that operates with international support, but faces the same structural resource constraints. Papua New Guinea, which sits on one of the most volcanically active stretches of the Pacific Ring of Fire, has monitoring capabilities that are genuinely inadequate for the hazard. The point is not to assign blame. The point is that the El Niño volcanism connection, if it is real, and the evidence increasingly suggests it is, means that volcanic hazard is not randomly distributed across the El Niño cycle. It is concentrated during specific climate phases, in specific geographic regions, affecting specific populations. If you know that El Niño events are associated with elevated volcanic activity in the Western Pacific 6 to 18 months after the peak, then you know when to deploy enhanced monitoring resources, when to pre-position evacuation assets, when to brief emergency management agencies in the relevant countries. That knowledge is actionable. It could save lives, but only if the monitoring infrastructure exists to take advantage of it, and only if the coordination mechanisms between climate scientists, volcanologists, and emergency managers are robust enough to translate the scientific signal into operational response. Right now, those coordination mechanisms are nascent at best. The climate modeling community that tracks El Niño and the volcanological community that monitors Pacific volcanoes have not historically operated as a coordinated system. They attend different conferences, publish in different journals, use different models, speak different technical languages. That is changing, slowly, pushed partly by the research we have discussed tonight, and partly by the 17 eruptions of 2024-2025 that have given the connection between El Niño and volcanic activity an urgency and a visibility that the academic papers alone could not generate. Was the 2024-2025 window, the event finally forced the integration of climate and volcanic hazard monitoring? Or will the scientific communities return to their separate silos when the immediate episode recedes? The answer to that question will determine how ready the world is for the next El Niño. The 2023-2024 El Niño event has passed its peak. By mid-2024, ENSO indices had returned toward neutral conditions. The tropical Pacific is in the process of transitioning, potentially toward La Niña, which typically follows strong El Niño events. La Niña has its own relationship with volcanic systems. During La Niña, the trade winds strengthen. Warm water is pushed back toward the Western Pacific. Western Pacific sea levels rise. In principle, this would suppress the unloading mechanism that drove elevated volcanic activity during El Niño. The historical data supports this in broad terms. Volcanic activity in the Western Pacific Ring of Fire tends to be somewhat lower during La Niña years than during El Niño years. But the relationship is not perfectly inverse, and there are important exceptions. More importantly for the current situation, the volcanic systems that were activated or perturbed during the El Niño window do not simply return to their pre-El Niño state when the circulation pattern changes. They have been pushed. They have absorbed a perturbation. Some of them released that perturbation through eruption. Others did not. The ones that did not release, Ruiz, Taupo, Campi, Flegre, Aniakchak, and others, are sitting at a higher baseline of accumulated stress than they were before the 2023-2024 El Niño. When the next El Niño arrives, and based on the historical pattern, another significant ENSO warm event will likely develop within 3 to 7 years. Those systems will receive the next forcing pulse from a starting point closer to their eruption thresholds. Each El Niño that perturbs these systems without driving them to full release may be loading them incrementally. The system is ratcheting upward. Not uniformly, not predictably, not on a timescale that makes specific forecast possible, but in a direction. The climate models that project future ENSO behavior under greenhouse warming generally suggest that El Niño events will become more intense, though not necessarily more frequent, as the climate warms. The physical reason is that the tropical Pacific contains more heat energy in a warmer world, and El Niño events, which are driven by that heat energy, express it more intensely. A more intense El Niño produces a larger sea level anomaly in the Western Pacific. A larger sea level anomaly produces a greater unloading perturbation on Pacific volcanic systems. A greater unloading perturbation drives a stronger volcanic response. If this scaling holds, and the research suggests it does, at least in principle, then each successive strong El Niño in a warming climate may produce a stronger volcanic response than the equivalent event in a cooler climate. The 17 eruptions of 2024-25 may represent the floor of what to expect in future El Niño events, not the ceiling. That is the projection. That is what the science, taken seriously and followed where it leads, says about the future. Was the 2023-2024 El Niño the beginning of a new pattern of intensified El Niño volcanic coupling, or was it a one-time coincidence of unfortunate timing? The data from the next El Niño event will be the critical test. and the scientific community will be watching. I want to spend a few minutes on the alternative narratives that have circulated around the 17 eruptions because they deserve a direct response rather than dismissal. The most widespread alternative narrative attributes the simultaneous volcanic activity to geoengineering, specifically to stratospheric aerosol injection programs that various governments or private entities are allegedly operating to modify the climate. The theory holds that these aerosol injections are destabilizing the volcanic systems below them, either through direct chemical interaction with crustal rock or through thermal effects on the atmosphere above volcanic systems. There's a kernel of real science buried in this narrative. Stratospheric aerosol injection is a real proposed geoengineering technology. It has been studied extensively as a potential method for reducing global surface temperatures. Small-scale experiments involving aerosol injection have been conducted by researchers at Harvard and other institutions, but the scale of the proposed experiments, grams to kilograms of aerosol material in highly controlled releases, is separated from the scale. Required to influence volcanic systems by a factor of roughly 1 billion, the energy required to alter the thermal structure of the atmosphere above a volcanic system in a way that would influence magmatic behavior at 5 to 2, 0 kilometers depth is not available to any existing or proposed geoengineering program. More fundamentally, the geographic distribution of the 17 eruptions follows the El Niño sea level anomaly pattern almost exactly. The volcanoes that activated most strongly are in the regions of greatest western Pacific sea level drop. If geoengineering were the cause, you would expect a different geographic pattern, one related to the location of the alleged aerosol injections, not to the location of El Niño-driven ocean circulation changes. The data doesn't support the geoengineering hypothesis. It supports the El Niño loading mechanism. The second alternative narrative attributes the simultaneous eruptions to a geomagnetic or solar influence. The idea that solar activity drives volcanic activity is a recurring theme in alternative geological communities. And like the earthquake version of this argument, it fails on physics. The energy in solar magnetic field variations is transmitted to Earth primarily through the geomagnetic field and through the ionosphere. The depth at which these electromagnetic effects can penetrate the solid Earth, the depth at which they could conceivably influence magmatic processes, is measured in meters to tens of meters, not in the kilometers to tens of kilometers where the magmatic systems of the Ring of Fire operate. The physics of electromagnetic penetration into conducting rock simply does not support the proposed mechanism. What the data supports is the El Niño loading mechanism, sea level change, oceanic mass redistribution, pressure perturbation of volcanic systems that are already near their critical thresholds. A physical mechanism that operates on the right spatial scales, produces the right geographic distribution of effects, and fits the historical record of El Niño volcanic correlations going back 3 centuries. The real story is complicated enough. It connects ocean circulation to volcanic activity through a mechanism that most people